Okay, are we ready to go? We're going to have pointers today. Everybody's favorite topic. And I'm going to wait because half the people are going to show up until halfway through this lecture. But at the end, I'll go over the final exam schedule that's coming up. But I'll wait with that. Keep making the mistake of doing it first, and then half the people show up, and then I got to repeat it at the end. So I'll just wait to do it at the end. So how many people like working with pointers? It's the response I expected, actually. Complete silence. The first time this class has ever been quiet. I know. I think some people over here said they loved it. An exercise of destroying your computer. Not really. Pointers are fun. I don't know why people don't like pointers, but C++ has pointers in it. I think they're great. I love pointers. And so here's the issue. If you're a Java programmer, you've never seen this before. You're never going to see this again unless you program in C++. But pointers come in handy. They could be your worst nightmare. It comes from a pointer misuse here, this linked error. That's an old message. It looks like it's from Windows 95 or something. It brought back memories. Oh, what are we talking about? Let's look at memory. If we could actually see what memory looks like, it might look like this. Might not. The ones in blue are the memory addresses. So here we have the addresses 1, 2, 3, 4, 5. Yeah, as if it were sequentially numbered. And the black that's in the box is a value that's being stored. So when we use integer I, we go out there to, like, say, number 4. So make I equal to -0 or something. And then we put -0 in the box. So we're doing the same thing with pointers. We're just accessing the address instead of the value sometimes. So when we declare an integer, here's my int. We come out, and it chose space number 25. And it put the value. In fact, if you declare my int, integer my int, and you don't give it a value, it's going to take whatever we used to be there, which is -4717. Where that came from, I have no idea. It's garbage. It was sitting out there on the computer. Last person who used that memory address, had that value there. So by declaring an int, you've taken up just enough memory to hold an integer, and you don't know where in memory that's going to be. You never know the address, actually, and you don't know where it's located. Computer just picks a space at random. I'm sure there's a scheme. There's an algorithm that the operating system is going to use to allocate the memory. But the value is at some memory location. And we can print the value out. And the value here, if we printed it out, would be 4717, which is garbage, as we've seen before. So we copy 42, let's say, into the section of memory that we're calling myInt. And we say myInt is equal to 42. And so now it goes out to myInt, which is at address number 25. And we're going to put the value of 42 in there. So now we've got 42. This you've done so far. You've done this every time you created an integer, or every time you did something. Here's the new part, pointers, which is nothing different, really. Allows you to get at the address, but we don't actually even work with the address. We just ask for the address. So the address of where the information is located. And similar to call forwarding in a lot of different ways, you ask the pointer where to go, and you go there for the information and you get it. So to create a pointer, we use this asterisk here. Oops, here it is. This asterisk is called a dereference and a reference. It's both. And I think that's where C++ went wrong, because if they had used two different symbols, it may have been a little bit more clear, like a caret symbol or something instead of the asterisk. But no, we have the same symbol. It means both. So it follows the format of the data type and the name. An example, integer with this little reference, PTR, which created a variable called PTR, and it's a pointer type, and it's holding enough space to be allocated for an integer. That we've seen so far, actually, in a couple of the examples I've given you. So now when we declare an integer pointer, it called this space pointer. The name's the same. The identifier is always going to identify a memory address. And now it's going to, essentially do the same thing as integer I did, or integer my integer. So it found a space. So now what we have done, we've created a new variable of the type PTR that points to an integer. Notice that we haven't initialized the pointer to point to anything. So we want to have it point out. If we printed it out, we're going to get garbage, essentially. If we printed out the value of PTR, we're going to get 98131. It gets printed out. So, which is kind of garbage, but this should really hold a memory address. Because what this is going to do is point to something. And we're going to, in the next slide, we're going to point it to my integer. But the purpose of the pointer is not really to store value. It's to store a memory address. So how do we get the address of my integer so that pointer can point to it? So what we're going to accomplish eventually is two variables that are both pointing to the same memory address. Remember that you can still access the value of my integer directly. So you can say integer, some integer equals my integer, and copy the value, use it. We can still use the original integer that we created, even though we're going to use it with this pointer. So what we really need is a pointer to store the address of where my int is located. We do not need to store the value of my int for the pointer, just the address. So this is where the address of operator comes from. So we use the address of operator, this ampersand, to get the address of where the variable is going to be in memory. And what would the following statement print to the screen? The address of my integer is going to print out 25, because that's the address that we arbitrarily picked here. In the next slide we see that it says 25 is the address of it. If we just said print out my integer, we get 42. The address of the ampersand right before it, we get the number 25. And what we really want to do is make PTR 25. We want 25 in here. If we have 25 in here and we follow PTR, it goes down to here. Now we have two variables sharing the same memory address. This is what we're accomplishing with the pointer. You might be wondering, well, why do we even want this? Why do we even bother with this? This enables you to access the same memory location from different variables and juggle the variables around without actually having to make a copy of the data. We're not moving anything. We're not moving my int anywhere. Instead, we're just going to access it through different variables. And you're saying, well, why do we want to do that? Well, we could use it to send information to a function, return it from a function. We don't have to return it from a function. We can have it go to a function, and in the function it permanently gets changed, sort of like arrays do, right out here. We can use it to create some data structures like linked lists and stuff. So dynamic arrays, all sorts of different things that we can kind of create. And the pointer concept enables us to juggle the memory around without having to copy it here, copy it here, copy it here, which makes it faster, makes it a lot more efficient, which is why pointers are part of the language, actually. So we get the pointer to point to something. So we know we need a pointer to point to my int. So here we have pointer is equal to the address of my integer. So PTR is not equal to 25. So the pointer is the pointer, so it expects the address to be assigned to it. And here we get the address of where my int is stored in the memory. We copy it to PTR. So, good so far? See, pointers are easy. I'm going to show you some code and you're going to go, why is this more hard? And why is this more difficult? It's not difficult. It's just getting used to the concept, not being afraid of it, I think. That a lot of students, especially undergrad students, the first time they see pointers, they spend half a semester looking at pointers, and then they realize, well, why is it complicated? why is it so hard? It's not hard. It's easy. That's my theory, and I just say it's easy. Everything you say is easy, essentially. If you say it's hard, it's always hard. So life should be easy, right? Just the same way as everything is fun. All right, except for that. Doesn't sound like fun. All right, so here's the before, and now we have the after, where we've got PTR is now equal to 25, which is the address of my int. So this is what the statement is actually doing. So we're pointing to, PTR is now pointing to my int. So what would this do? What would this do? PTR is equal to my int. It would make PTR equal to 42. And what's at 42? Where's 42? Here's 42. Negative 4717. Oh, that wouldn't be good. So this is going to be equal to the value that my int is storing, 42, which is not what we necessarily want. There's 42 here. So PTR now would be equal to 42. Wrong memory address. So leaving out the ampersand and just making it equal to my int instead of the address of my int causes weird stuff to happen, and this is one of the problems we get with pointers. It's like assigning it to the wrong memory address, the value instead of the memory address. And then we go point to it, we follow the pointer, and we go to cell number 42, and we get the wrong value. And then we go, well, how come the program's not working? So, tricky screens of death. These would be called blue screens of death. I took that out because they're no longer blue. They're different colors now, I guess. Actually, I think the screen's now black, but let's see. Last thing to learn is how to dereference a pointer. So this means to follow the pointer. So unfortunately, we use the same operator as I mentioned before, the asterisk operator. So cout, print out, follow PTR. If we follow PTR, PTR is equal to 25. We follow 25, gives us what's in the space 25, which is the value of 42, if you remember from the previous slide. We can also do the same thing by printing out my int, if we wanted to. So we can use them both still. So we can juggle around the list a little bit if we wanted to. So follow whatever PTR is pointing to and print out the value that it finds at that particular location. C++? Yeah. Okay, so follow the pointer and print it out. So here we have, and the value that 42 is going to be printed to the screen. So here's another example. And for those of you who just walked in, we explain what the grid looks like here. The blue is the memory addresses, the black is the value, and the red is the variable name that we're going to be working with. So, and this is our fake memory, as if we actually had a view of what memory actually looked like. So, but this is an abstraction of it. So let's declare a pointer, integer asterisk pointer. Now I purposely moved this around a little bit. Before I had the asterisk over here, and then I had the PTR over here. I sort of like this method. A lot of people don't agree with me, though. They like the other method. It doesn't really matter, actually. All you got to do is stick this asterisk in between the data type and the name of the pointer. You can even put a space in here, but it looks like multiplication. It looks like int times PTR. Not such a good thing. In fact, a lot of the older compilers aren't going to take it either because it looks like multiplication.
If you put a space after the asterisk, will you not take the compilation error?
If you put a space here in the current modern compilers, you probably will get a compilation error. If you put a space in between before and after that asterisk, yes.
The compiler accepts that it is a math.
If the compiler thinks it's a math operation, you're going to get an error. So if you put it close to here without a space or here without a space, it works just fine. I like it here because really the data type is integer, but the variable name, I say a lot of people disagree with me. They say, well, the data type's a pointer. It's a pointer integer, so put it over here. And then the integer name is PTR. Whatever. So that it makes it hard to read code because you have that option, which is kind of the nature of C++. You have so many options. Okay, so we have it decided, and usually somebody asks, well, how do you know it got 10? Last time we had 25 going on. Well, it decided to put it here. Who knows? You can't decide this. You can't pick it out. You never know where it's going to go either. So it picked space number 10, which has the current value of -6. And we don't know what it's going to have, actually. It's going to have anything. So what would happen if we followed PTR? If we followed PTR to -6, I don't see a -6 on the board here. Where do you see 36? Do I see -6 on here? No, this is saying the memory address. The blue is the memory address. It's going to look for, it says follow PTR. Okay, PTR is pointing to -6. Follow it. We don't have a -6 memory address, so it's going to be confused. I mean, this is what happens. We have the blue screen of death. No longer blues from what I've been told. So, now I think it's a black screen of death. I don't know. Long story short, there's no -6. If there was a -6, if there was, we'd get whatever was there, which may not belong to our program, actually. It might belong to somebody else's program. You can possibly see how the process that's running this program could possibly read or write out of its memory assignment, so it could possibly cause an operating system error, is the point that I was trying to make. Why do I need pointers? Because pointers for passing parameters only passes a copy of the function. You can't change the mains variables in a function. When you send something by copy to a function as a parameter, what happens in the function stays in the function. You got to pass the argument back. What if you're working with a lot of data? You want to pass a lot of data to the function? Probably not. It's a lot easier to pass the location of the data. So the pointer allows you to easily pass information to functions and have the function change the information permanently and affect anything outside of main. So it breaks the rules of going to Vegas, essentially. So what happens in Vegas doesn't stay in Vegas, it comes back to main. So void cannot change integer x. Something happens with x, great. And this is the program where, we're not using pointers. Out here in main we have integer, my integer is 17, cannot change. Send 17 to here, and prints it out, nothing changes, everything's good. If we declare my integer here, the parameter passing only passes a copy of the function, can't change the main variable's information. So integer, this is going to step through the program essentially. Integer, my integer 17. Oh, here we go. We found memory address number 7. Called it my integer. It's holding the value of 17. And then now we're going to pass it to cannot change. And when we pass it to cannot change, the number 17 comes up. So that's why it's called by value, because we're passing the value of x. My integer. And we're passing it in and assigning it to the value of x. So x is now equal to something, and then x gets printed out to the screen. Great. So we print out x up here, integer x. And we actually create memory. When we say integer x, we create another variable out here. And we've assigned it a value. And now we're using this variable out here. We're not using this one anymore, which is why it's a pass by copy, or by value versus by reference. And then if we print it out to the screen, we're going to get the number 6. And now if we go down, we print out my integer, we're going to get the number 17. It's printed out, because that's what each one of them is holding, actually. Now with pointers. So you see here in the function call, we're saying take it in as a pointer. And over here we're saying integer pointer is the address of my int. So we could have just sent my int actually, but instead we're going to create a pointer along with my int. So what we do here is we say in integer my int is equal to 17, same line as before. It went up to 7, decided to put 17 in the value for that particular location. And then we said, and then here I switched, I purposely moved it over for you, so now we say integer asterisk for those people who like it over there. Pointer is equal to the address of 17, the address of my int. So we get down to my int, say that what's the address? It's 7. So 7 comes back up here and it gets assigned to PTR. So now PTR is equal to 7, which is cool. And then now we run the can change function and we set it PTR. This is what confuses everybody. PTR is a pointer. It's the name of the variable that's a pointer variable. We don't have to do anything in here. We just use like any other variable. But we have to remember that PTR is storing a memory address. And so PTR is storing number 7. So we're sending 7. We're not sending 17 or anything else. We're not following 7 to 17. So when we send PTR, we're sending the number 7 up here. And number 7 up here is being treated as a pointer. So it says follow 7 and make it equal to 6. So if we follow 7 down here, it's going to point to the my integer variable after we've created it up here, because we have x now. I'm sorry, that was pointer. We have x over here, and it's also equal to 7. When we sent it up, we now have it equal to 7. When we follow it with this step, this makes it equal to 6. So now we have 6 down here. So that's the kind of logic that's used. Nifty, handy for linked list. Linked list is nothing more than a bunch of pointers. Create a bunch of pointer variables called nodes, and and the node could be a structure or a class or something, and it carries two things. It carries a value, and then it carries a pointer to the next memory address. And they call it a linked list because each node only knows about its neighbors. So one item in the list follows the next, and it goes to the next neighbor, and then that person follows to the next neighbor, to the next neighbor. And all the data items are linked together, so you can break the link somewhere and reattach it somewhere else. And you can easily move items around without having to rejuggle the whole list. And you're manipulating the pointers, the variables for the pointers is what you're doing. And they're not really holding any data. You're not moving any data around, changing anything. So it's real quick. It's really efficient, actually. So if we follow X and print it out, we're going to get the value of 6 printed to the screen. If we follow my int, actually we just print out my int, we get 6. So if we use my int now, it's permanently changed. We changed it through X, because X was pointing to memory address number 7, and we changed it to 6. Not so hard. Good. Interesting note. So, at this point, there are 2 statements that print out the same thing. We have, if we follow PTR, or if we print out my integers, as we saw before, these do, so do these, actually. If we print out PTR, and we print out the address of my integer, well, they're both 7. The address of my integer is 7. PTR is pointing to 7. So we're printing out the addresses, which is answering the question, why are they the same? Because they're both pointing to the memory address 7, essentially. Which means, actually, we can use them both the same, and whatever we change at memory address 7 changes for both of them. Which is where things get kind of tricky sometimes. So, summary of the pointers. To understand pointers, you need to understand memory. So the ampersand is the secret to it all. That gives you the memory address. You create and dereference using, I like to say reference and dereference, but it's usually when you reference it, you're creating it using the asterisk. And passing a pointer to a function can make changes to the main. So it allows you to change main information. Questions on pointers before we apply them? No, I never get any questions, so that's really good. So let's talk about this list, this linked list, the stacks and stuff that I've been talking about in terms of putting pointers to use. What's a linked list? This is stuff you don't get until unless you take a data structures course, and if you don't have an undergrad in computer science, you've never had this before. Because usually don't get in business classes or anywhere. Other types of majors. But it comes in handy because if you know the data structures, then what ends up happening is you can apply them. And now that you know what pointers are, hopefully, then you take pointers and implement these more complicated, more useful data structures. One of them being a list concept. And in Java, it's really easy. You just import the list. They have linked lists already built into the language. C++ doesn't have it. It's up to the programmer to make their own linked list. So a list is a collection of data elements in an array structure. So from any given element in the array, the previous and the next items can be obtained by using the addresses of the adjacent memory locations for each of the other items in the list. As I mentioned before, each node or item in the list knows about its neighbor, and so we ask for its neighbor, and the neighbor knows about its neighbor, and that neighbor knows about its neighbor, and so forth, which is how we list things together. And that's really what's called the linked list. So it's a collection of data elements. The locations of each element in memory is only recorded by a pointer to the next element. And the data elements may happen to be adjacent in memory. They may not. They could be all over the place, actually. But you can't rely on that. So let's take a look at it. We talked about arrays already, and we have a simple array structure here. And we know that the name of the array normally stores the starting location of the array. And then we say if we want an array of 5 elements in this particular case, and we want them to be integers, we get 1, 2, 3, 4, 5 integers. Usually the array structure, because it's implemented in the language, are storing adjacent cells. And we know we have index values, a little review, 0, 1, 2, 3, 4, that are associated with these 5 cells. And if we want it, we just say whatever the name array is that we created, and we say, give me item at 0, give me item at 1, 2, and we retrieve it. Limited. If we want to populate the array, we have to use like a for loop normally to go through and assign values. We have to clear out the array manually to use like another loop to go through and get out. It's not very efficient. It's kind of structured. So the linked list here, we might have 5 elements that are simple integers, but there's no relationship between the elements. We just have 5. Consider them 5 separate memory locations, 5 different variables, and we're linking them together using pointers. So this is not showing you the pointer implementation, it's just showing you like 5 random spaces out there holding numbers, and it can hold the same items as an array list does. So are just sequences linked lists themselves are just sequences of data that's linked together in the memory using pointers. So each element in the list is made up of data plus the pointer to the next item in the list. So you have some interesting combinations. You can add items to the list from the start of the list or from the back of the list, or the front or the back or rear of the list, because we could put it in the middle if we wanted to, but we normally pick a side and we add items to the list by saying, okay, you're equal to the next one, and you're equal to the next one, and you're equal to the next one. And then we just keep piling them up so we all link them together. So the node, and this is, I've used this terminology already, but let me just define it for you, is the common name used for the data plus the associated pointer. Why do they call them nodes? I know sometimes you call them items. We call it an item, a node. So it's more than a single item, though. We have to use a complex data type for it. So we can create nodes out of, it's common to see classes, common to see structures. Because if you created a structure, we covered those already in this class. Structure contains multiple data types of different varieties. We could give the node a name if we wanted to, like item 1 or something. But we can also give the node a data to store, an integer value if we wanted to keep a linked list of integers. We can give it a double of floats. We can give it anything we want, actually. So the node can carry different data types at any one moment of time if we have a structure, let's say, that supports that. And we can also, obviously, we're going to need to give the node a pointer, and the pointer is going to be to the next node, so it knows about its neighbor node. So you can create a linked list that carries multiple data types in it. Extends the capability of the array, because remember, arrays only hold single data types, and to get around that you have to create multiple arrays and use them in parallel if you want doubles and floats and strings. Now I can say, we can create a node that can consist of almost anything. It could be a structure, it could be a class, and we can put anything we want in there. In fact, we can even have, instances of objects that are linked together, and then those objects can run methods on the other items in the list if they wanted to. So that's what we're going to see examples of coming up, of that concept sort of extended out. Oh, what do we got here? Many kilobytes of data, names, addresses, student IDs can all be stored in each one of these nodes, as I mentioned before. I just went through that. So we chain them all together. The chain is as strong as its weakest link, just like the TV show. So we lose one of the nodes, we've lost the list, because they're all holding the hands together, and we break one of the hands, and poof, there goes the end of the list. Which actually happens in programming sometimes. So simply, if something is erased or corrupted, the node is in the middle of the list, the nodes are going to be lost. So let's talk about a couple different types of lists. We have first in, first out, last in, first out. We're looking at stacks and queues, if you think of the concept. If you can remember what a stack is like, if you just imagine plates. You take plates out of a dishwasher, you put them in a cabinet. So you put the first item comes down, and so that's first in, and then the next item comes on top of that, next item goes on top of that, and then when you pull the plates out, no one picks up the stack. To pull the plate out from underneath, you're going to break all the plates. If you do that, you're going to break everything, and especially if the stack's pretty big. So you pull from the top of the stack. So the first one in is always the last one out. So the first in, this is not even on the list here, but because I'm talking about a stack right now, but that's different than a queue. A queue is more fair. A queue is, if the first item gets in line, and then the next person is like a bank queue. The first item who waits in line is the first person who gets waited on. Second item is the second person, third. So that's more of the first in, first out combination. Or we get the last in, first out, which would be the stack actually. So the last plate that gets put on the stack is the first plate that gets taken off the stack. And that actually causes problems. An example, the stack of papers here. When you put some papers on top. I like plates because it's easier to visualize. And then the example here would be the supermarket checkout. I like the bank. Supermarkets are stressful places. Actually so are banks. So. Alright, and these are different descriptions that describe the behavior of the list in general. And we implement this in our linked list data structure that we create with our pointers. So we can kind of get the order ourselves. So all are last in, first out in this particular lecture, but you can easily turn them around. So instead we're going to go, we're going to create stacks essentially and add to the top of the list. If you added it to the bottom of the list and you pulled off the top, then you'd be in a last in, last out. So it depends on which end of the list you're going to add the items to and which order you're going to take them off of. You can use any of the combinations, they all work. So you're going to build all linked lists in a last in, first out queue. You can easily make them all first in, first out instead. As an exercise, if you want to understand it, you can convert all of these examples to first in, first out if you want. So building a basic linked list, let's do that. So we're familiar with structures, we've seen this already. We're actually familiar with classes already, I've gone through all that. Haven't hit some of the inheritance stuff from what I hear, but let's talk about the node here. So we're going to use a type define, a float. Well, we could have just called it a float list element. So what are we going to store? The list element is going to be a float value. So this is the data that's stored in the node. We're going to have a list of floats. And the pointer to the next one, so the node, which is of the same structure type. This is the data type node that we've created and we're calling it node. It's a structure data type. The node, we're going to call it next. So, and it's a pointer, which means we're going to create another piece of data and we're going to point to it. And it's going to hold next is going to hold a memory address. Same as those other examples I just went through a few minutes ago with that fake little memory map. It's the same concept actually. So we're going to hold an address to point to. So the trick is assigning it actually. So that's the basic building block of the node. And we're going to stick the node inside of a class. So here's the list. So we have the node, which are each one of the individual data items. That's a simple one because it's only holding a float. We could create a node of students if we wanted to and have first name, last name, GPA, stuff like that if we wanted to. We can hold more than one piece of data, that's what I'm saying. But we always will have to store at least one of the next. This makes no sense to store the previous, although I've seen nodes that do that. Because then you got more to update. So if you switch the order around, all you got to do is swap the nexts around. If you got a next and a previous in there, you got to update it after you put something in, and then you got to update it again every time you move it, and it's just too confusing. And really, why is it even needed? All we have to keep track of is the next item in the list. And if everybody knows about the next item, then they can all grab each other's hands and go together, kind of thing. So basic linked list, we have 4 functions that we're going to put in here, and here's our class, and we're going to call the class a linked list. So now we have a class that's created to establish the list for which it's going to hold nodes, and the nodes are structures. It was purposely done this way to show you that you can use nodes or classes, structures or classes for the list or for the nodes. You can do them all in classes, you can do them all in structures. Common to see classes used, however, for linked lists, and then structures used for the nodes. So, okay, so we have some private data. We have a node first. We're always going to have either a first or a head. You can call it a head or a tail, which is the back of the list. We got to keep track of one, the head or the tail, because we have to add the items to the front or to the back of the list. So we got to keep track of one or the other. So node is the pointer to first. A variable we're going to call, it's a pointer variable we're going to call first, and it's a pointer variable. It's going to store a memory address. And then we have a constructor linked list. And we're going to add a node into the start of the linked list, because we're going to use the first item here. So we're going to have this method here. It's going to say void insert node. And it's going to take, the method's going to take a parameter. It's going to be the list element in value. So here's what we're doing here in terms of the basic structure. So once we have set up the class member functions, and we created the main program, the driver program to do this, we use the linked list class, or the linked list. Could be visualized sort of like this. We have the first. The last is always going to be null. So if next points to null, we know we're at the end of the list. Same logic as a string, actually. And believe it or not, strings are implemented just like this. It's a character list. a string as a character list, actually, with null at the end. It's not treated the same, but if we get the address of the starting string just like a character array, it's sort of like, you kind of see it's stored sequentially, because when we assign it sequentially. So it's stored like an array, treated sort of like a pointer. It's kind of a hybrid between a pointer variable and an array, actually. This is kind of interesting. So we have the beginning of the list, we have the value. The value on the top is going to be the float value that we're storing, because we have this list for some reason. We're storing a list of floats. And then the next value. And if it points to null, we're done with the list. The list is over. So we can search for null. And if null exists, we know we're done. We don't have to worry about how many items are in the list, because we don't know. That can grow dynamically, actually. So here's the constructor, and this should maybe look familiar at some point. The constructor is going to create an empty list. It's going to say when we create a new instance of this list object, we're going to build the list and start with 0, which means the first element is the last element. There's no items in there. So here's our empty constructor, our body of the default constructor. It's going to say first is equal to null, because we've started the list and it's empty right now. And this is the linked list constructor, scope resolution of linked list, the class that we just looked at. So let's create some functionality. This one's going to be the insert node. So we have to have something that, I have to have a method to insert into the list. So now we're going to add a node to the start of the linked list. In terms of our method implementation, this is what we saw already, the element that's going to take in the list element, which is nothing more than a float value, because we did a type defined on that. That's what the type defined for this data type is actually meaning. In value, it's going to be the value we're going to give to that float. So here we have node, pointer. So I'm going to point a variable new node is equal to, look at that, new node. So when we use pointers, we have two words, I don't know if I've mentioned so far, the new and the delete. When we allocate memory to use for pointers, we have a couple of different techniques. What we saw before was creating a pointer and assigning it to a variable, remember my int, and we assigned it to that variable that already existed. It was already created by the compiler. When it doesn't exist, we create new node, which is essentially going to create a new instance or new object, node object of type, the structure data type that we created in a few slides back. And new essentially is the key word that's going to essentially allocate that memory. So we can say new integer, new float, new node, to create a new instance. And now we have a pointer variable pointing to a piece of memory. And so we can store the value in the node. So we have a new node, and then remember before when I was talking about structures and classes, actually it was classes, I'm sorry, and I mentioned there's the dot notation to get at the values. And so whenever you're using a pointer, you can't use the dot, you have to use the arrow instead. So here's an example of that coming at. New node is similar to the dot, but it's only because it's a pointer that we're talking about. Value is going to be equal to the in value. And the in value is that float value, actually. So this is the value for new node. New node is going to equal to this new memory that we've got established. And then the next node is going, the next node is in the list is currently the first node. So we added a piece of data before the first, and it points to the first. Because we're adding the data to this top of the list, to right before first. And then first is going to be equal to last, or going to be equal to null, I should say. Some people like to say last. I don't know, way to last, first and the last. The way you design this is totally up to you. So the next one is going to be equal to first. So you make a new node with a new first node. First is equal to new node, essentially. So now we have, oh, okay. So now we have the first is equal to new node, which means it is the first item. So basic list operations. Now we have an overloaded output operator. So we have the output operator that we're going to overload here. Actually, you know what? I'm going to skip the overloading because I'm going to cover it next week, actually. Let's forget about, can we get through it without? Yes, we can get through it without this. Let's skip overloader operating for right now because I'm talking about pointers today and I want to keep focused on pointers. We'll hit that next week, actually, because there's a better lecture I have on that. So that one is just going to, we don't need it for anything. It's going to overload, well, let's leave it alone. Here's our main program. It's going to be my main driver program, simple main. And we're going to create a linked list, which is going to be my list. So my list is going to be defined as a linked list, which is that class. We're creating a new instance of the object. And then now we're going to say that the add a bunch of nodes to it. So we have my underscore list dot insert node 1.1. So this is running the constructor that takes the float value from the command line argument, adds it in, and assigns it to the value that's going to be associated with each float that each node is going to be storing. And then we're going to display the list. This is the overloaded operator that, let me talk about it, I guess, to display it. When we overloaded the directional operator, what we've done is we've said to print out using the, to display each node's value and then point to the next node's list to essentially give us that ability to traverse through the list to follow the nexus. So what that's doing is it's giving us the ability to print out my list because we've changed the functionality. When we overload an operator, it means we're changing the functionality. And in terms of overloading operators, not such a good idea because people love to overload operators like pluses and minuses so that you can change, let's say, a plus that does addition to concatenation. And then you use plus in the program and it's been overloaded, but you don't know it's been overloaded, and now you get 1 plus 2 and it equals 12, which causes problems. In this case, in this particular example, we're overloading the output in directional operator so that we could print out, display the list, changing the functionality, so we'll display the entire linked list. Otherwise, we can't just say print out this address. It's not going to print it out properly. So what's really happening? In terms of the code, to kind of go through it from a diagram point of view instead. We declared the linked list. The linked list was my linked list, which is kind of easy. We simply set first to null, so it created an empty list in the default constructor. We also have a pointer pointing to that null memory address. We inserted the first node. So when we said 1.1 in this previous example, when we said, insert node, this one, this one, this one, put 3 nodes in. It added 1.1 to the value of the float, and it said next is equal to null. Okay, and then when we added the second item in, the 2.2, it says, well, first is now pointing to 2.2, next is now pointing to 1.1, that next is now equal to null. So what ends up happening is every time we put one in, it comes to the front, and then the links just get added. So this is going to stay the same when we just put, 1 point, is it on here? No, it's not on here. We put in 3.3. First is now pointing to 3.3, which is now pointing to 2.2, which is still pointing to 1.1, which is pointing to null. So we don't have to redesign, we don't have to reorder the whole list, we just add it in. So first points to the first element instead of the second element. So we can find all the nulls, the nodes with a particular value, and what we do is we now create methods to search through the list if we want to. So here we can find all the nodes in the linked list with a particular value stored in them, and this particular value is going to be something that we enter in on the when we call the method, like search for 3.3 or something. So here, now we can create a node, and we're going to put a node in, and then we're going to check a value, change the pointer to the next node to check a value, change the node. So we have this, if you can imagine a visual, like a train of nodes, and we have a node underneath it that goes from here to here to here. It goes through the list looking at the values that are stored in each one of the nodes. So it's outside of the list, but it's working with the list, which is interesting. It's just changing, it's leaving the list alone, because we don't want to reorganize the list. What we just want to do is search through it and find something in the list. So we have this underlying little bus that goes around the train and checks each one of the items in the train. And to allocate the working node, so we have a working node, I'm going to call it that. The node is going to be a current node. We could call it a current node, we could call it a working node, whatever we want to call it. we're going to make it equal to first, which means we're going to make it, put it at the top of the list. And then integer count is going to be equal to 0 to keep track of the number of nodes that we found. And so we could use this to actually figure out how long the list is too, because at this point we don't know how long the list is. We don't know how many nodes we've created. So unless we keep a global counter, we can do that in a class variable if we wanted to, actually. Skip through the linked list and list all of the nodes we find with the required value, and here we're just going to go. This is the node value, this is the, and then check the node value. So it goes through and says, is this node value equal to this value? No. So while current node doesn't equal null, and here's where that null comes in handy, because the current node is going to be the last node if it equals null. Then node count plus plus, so we're on node number 1, and we go to node number 2, node number 3. If the value, current node dot value is going to be, if it equals to the value we're looking for, then print it out. So if not, then go to the next. So here we said node dot next, which is basically going to say next node, next node, next node. So it pops from one node to the next node, and looking at the value that's associated with each one of the nodes. And then if it's not found by the time you hit the rest of the nodes, when the while ends, when it's doesn't equal to, when it equals to null, then print out no, it's not found, essentially. So here's an example of the usage to find all the nodes with a particular value. Example here, find all the nodes with the value 3.3. So we'll display the nodes in the linked list with the value of 3.3. If none of them are found, it's going to print out none found. So that's how we would look through. It's actually how we would actually count up if we wanted to, unless we kept a class variable, let's say, to keep track of how many instances were created of that particular class, which would probably be better, because then you could ask the class, ask the linked list, what's your count value? And it would tell you at any one moment of time how many nodes existed. We can also delete items from a list. So we could delete a node from the list. So we'll look at the function to delete a particular node. Remember, when we insert a new node, it's usually the new first node. So if we delete something, if you imagine that train of nodes again, we find the one we want to delete, pull it down, see what it points to, change the next here to the change the next here, delete the memory, and we're done. A little easier than you'd think, actually. So when you delete node number 1, you're actually deleting the first node in the list. So the first node actually has to be treated differently, because if you're deleting the first node, you have to have first point to it. So we know which node is the first one. So here we go. So we're going to delete a node from the linked list. We're going to allocate, delete, and previous nodes. So delete node is equal to first. Same thing as we did with the searching. I'm going to say that this node is equal to first node. And the previous node is equal to first, so we can figure out, because we have to move one ahead. Because we have to have this one, and then we have to have the previous one, and we have to actually have 2 nodes following the trail, because we have to find out where we're going to delete to, and then move over one, take this piece out, connect it to this one, essentially. So we have to keep track of 2 nodes. The one we're gonna delete, one right next to it or right before it, because we're deleting it from the front. We're going to do the previous. So we skip through the linked list to get to the required node. We find the required node. So here's the kind of the stop when there are no more nodes. Otherwise, find it. And we've got the delete and the previous going on. And then once we're there, we make sure that we're deleting a valid node, hopefully, and that the node number is larger than 0 if we're putting numbers on them. And then we delete the first node, make the first node point to the second node, essentially. So make first the second, and we got rid of the first. So you can easily create a stack concept where you push items onto the front of the linked list and pop one off just by saying, well, what does first point to? Take that one off. First now points to second, off. First now points to the next one, off. And keep essentially traversing through one at a time, node at a time, working with that concept. So delete the required node, and here's if you say delete and the name of the pointer variable, it follows the pointer to the memory and actually deletes the memory that it's allocated to. It does not delete the variable, just deletes the memory that delete node as a particular node item is pointing to. Delete node 0, if we follow through the functionality of this particular method, it was going to delete a number of the node that we've assigned to it. So we'll delete nothing. There's not a zeroth node number in the list. So delete node number 1, we'll delete the first node in the list, i.e. all the nodes inserted into the list. So it's using last in, first out. So it's deleting from the top of the list if we take this particular approach. We're going to say delete node number 2, it's going to delete the second item in the list of that nature. Delete node 50, delete node 99. So if you can probably tell at this point, for insertion and for deletion, we can insert anywhere we want. So let's say now insert number 5. So instead of in the old array environment where everything was constrained by a particular order of indexes, we have no indexes. So we can go through the list, find something, delete it, and we don't leave a space. We close up the space by changing the nexes, and then we can come in and insert anywhere we want. If we wanted to insert in this bunch of nodes, we just find the node where we want to insert it to, create the data, create the memory location, have this node point to this node, and then this node point to that node. So essentially insert the piece of data in. So some points on the linked lists themselves when working with a pointer data structure, such as a linked list. It's important to use a diagram sometimes, so you can kind of see what's going on when interpreting the code. Even experienced code writers will have logical errors. So if you diagram it out, map it out, a lot of people like to draw little boxes and little arrows and say, if this happens, then simulate what's going on with the pointer exchange. That way you can kind of figure out the logic. Because what you might think is happening might be something else. You might be deleting the wrong node. So what ends up happening generally when you first put it together and before you test it, or the first time you test it, it finds the node and then deletes the next one, or deletes the previous one, or deletes the wrong one, or it inserts it in the wrong location. It's just the logic, essentially. So also being careful when inserting and deleting nodes so the links between the nodes are not broken. Common problem when doing the insert and the delete is to break the list. And as I mentioned before, the linked list is only as strong as its weakest link. And if you break the list accidentally, the list is gone. Sure, you inserted the item, but the whole tail end of the list, it didn't get connected properly, so it's gone. So it's also crucial that you ensure that the code works with all of the nodes, especially the first and the last nodes in the list. Because sometimes when you do an insert or a delete, and it's the last one, how's it going to point to next? It's supposed to be pointing to null. So in some cases when you develop the methods, you have to have special behavior for the first or for the last, depending upon how you're organizing it. And you don't have to have both. You can just have a first, or you can just have a last. There's no rule that says you have to, and there's no rule that says you have to keep track of how many items are in the list either. If you make the class keep track of it, then you have the automatic count. If you traverse through the list every time you want to find the count, that's kind of slow. The purpose of creating the linked list is to make an efficient structure that runs fast, that allows you more capabilities than the array. So, in terms of the generic linked list class, let's start with an extremely basic class called animals. So we're going to make a linked list of animals, essentially. And then we're going to include the class in a linked list. This should be linked list class. And use the member functions of the animals class. So we can do inputs and outputs for animals, which is kind of interesting. So we can call methods, which we haven't seen yet. We've just stored single floats in the linked list. So this way we're changing a single line of code in a linked list class. We can make a linked list work with any kind of data that we want. So here it is here. Here's our class animal class. I used it in one of the other animal class examples that we created so far. Height, name, age, and the little constructor that creates an animal. So just like we had the nodes, but instead of calling it a node, we're going to call it an animal, and we're going to make it a class instead of a structure. So here's our generic linked list animal class, and our constructor again is going to just assign 0 values to finish out our class. And let's take a look at the class header here for our linked list, not the animal. So this is the list that's going to hold the instances of those animal objects. So we're going to use a structure node. And the structure node, this is what we saw before. So we're now storing animal data instead. So the value of this list item here, we just changed the list item to make it an animal. So instead of using a type define on a float for the list item, we made it an animal because animal is the class that we created. So this demonstrates an effective use of type define, actually. So let's say, for example, we created this generic linked list, and we created this generic node, and we decided that we were going to reuse this for every time we wanted to create a linked list. This is what we've done, actually. We've got this generic everything. And now we have this type define, and this is kind of an effective use of type define. We're going to call it a list element. But in the last example, our list element was a float. Now it's of an animal. So, you know, we have one line of code we changed. Now we have a linked list with nodes that store animal types and instances of animal objects instead of floats or integers or doubles. So not a bad way of reusing code, actually. Makes a generic, turns a generic linked list into a very functional list. And it's going to do the same thing. It's essentially a node, just working with it as a node. But the data that's storing is an animal instead of a float. So, and here we have same as the earlier lecture, same as what we've done here. First is equal to null. And this is the same. We get to store the values for the new node. Same as before, actually. And what you can do if you want to is you can cut and paste this code, stick it in, see a compiler, compile it up. Compile it, run it, play around with it, switch the order of the list if you wanted to, switch the items and the nodes to any class you want. Here's our main program where we define a linked list of animals. So and now we have inserted an item, and now we're going to display the items out. This is that operator that's been overloaded, so don't worry about that. So classes of classes. So far we've used classes of structures. We can also have classes of classes. So we have a class animals, which has private data and various different member functions. Then we can have we can include it in a linked list class, and with its own private data and its own member functions. And just like C++, we can manipulate the linked list when the linked list functions are called. We can call the methods, get the data members. We can essentially have a list of objects that are running. So if any of these linked list functions manipulate any of the animal data, then the animal functions are called automatically by C++ in terms of linked list items. So in exactly the same way, classes can be combined with extreme complex systems that can be built from this. And it kind of increases the power, essentially, of using classes and using pointers, essentially, in the language. So some of the most complex creations have been operating systems, as an example, are sometimes built with linked lists that are created in classes that store nodes that are class types, object types. And you can put different types of objects as well. As I mentioned before, we can have different types of nodes in there. We can have, if you wanted to, you can create a very complex node that does a lot, actually, put it all together. Network software, business applications, all sort of run that way. It's a little very brief introduction to stacks and queues, and I actually kind of covered this already, but to reiterate the point in terms of what we're looking at, they're really referred to as abstract data types, data structures. So stacks and queues are both of the same type of the abstract data type. So the stacks data is always added, and this is where the terminology comes into play. A stack has a push and a pop, where an item is pushed onto the front of the list and then removed or popped. And then terminology is used for that from the front of the list. And it's a last in, first out. Last in, first out, yes. I had to think about the stack of plates for a minute there. And here's our stack as a linked list as we look at it. And what we're doing is adding, we always add to the top, and the last one always points to the wall. So to get a particular number to stack, we need to keep removing values off the top of the stack until we find the one we want. And then the data is pushed onto the store. It's popped off to be removed. So you push it on, pop it off. Push it on, pop it off, essentially, which is how a stack actually works. And then these are the data items, and then these are the pointers to the next item in the list, if you've seen it. And the queue, in contrast, the queue's data, very similar structure, actually. Always added to the end of the list and removed from the front of the list. So we're not doing the same. This here, we're actually pushing on and pulling off from the same end of the list, which makes a stack actually kind of easier to implement in some ways, but the functionality is not necessarily what you always want. If you want a queue functionality, you got to work with both ends of the list. You add to one end and you pull off of the other end, which means you have to have two separate functions instead of just one function. Well, you have to have two separate functions anyway in a stack, but so you remove from the one front end and the other. So the type of data structure is called a first in, first out structure. So just like a queue as a supermarket or a bank. So here's our queue, if it would look like in a linked list implementation. For the queue front pointer, so in a queue usually you have a front and a tail, or a head and a tail usually, because the tail is the end, the head's the front, or front and end, however you want to call it. Or in this case, it's going to be front and null. So to get a particular number in the queue, you need to remove values from the queue on the left-hand side until you get to the required value that you're looking for. So here's the queue rear pointer and the queue front pointer. So it just means you got to keep track of the other end as well. So that was a lot of stuff on pointers, stacks, and queues. And we still have about a half hour left. I was told we didn't finish inheritance. Does anyone remember? Did we get halfway through that? That was lecture 7 we just went through. Okay. Let's go back down memory lane for a few minutes here. Let's see. Because I can finish that up today then. And we don't have to... Oops. There we go. Let's go down memory lane for a second. Topologies. It was the second part of this lecture, actually. No. Unfortunately, I have to pop through it all. And if you're still confused on the class concept, oops. Hello. My mouse got carried away. Alright, I know we started this. Did we finish it? No, that's what you're saying. Do you remember where we stopped? Well, let's just go down memory lane. We talked about the concept of inheritance, right? And we talked about mammals, dogs coming from mammals and chihuahuas and sheepdogs. And we talked about superclass and subclass, I believe. And we gave an example here of a sea dog and the sea dog C++. So to review your memory here, we have the implementation and the specification. This would be the .h files would be the specifications. The .c++ files would be the implementations, where we're implementing the behavior that's specified. And when we include files, I think I remember where we stopped. It's about right here or so. So when we include files, we include the .h file, actually. Because why don't you include the whole thing? If the object is already created, because usually by now I get students asking me, well, how can we have to use 2 files? Well, why do you include string.h and iostream.h and stdio.h and all these other things that you've been including so far? It's because you're including the specification. The implementation is in a .o file. It's called an object, compiled code. If the class doesn't change, why recompile it every time you compile a program when there's many different classes that are being used? So we include the .h. In this particular example in CDOG we are including the .h. Well, we can include this .h in other files as well. And when you do that, the compiler will go out and look for the object code. If it finds the object code, it just includes it. It doesn't have to recompile it. You don't have to do it this way, but this shortcuts the compilation process and makes it more efficient and guarantees that you have the last known version that was compiled correctly, hopefully, and everything works out just fine. And you don't have to include all the source code, all the implementation. It doesn't really matter. So In this example, we were taking, this is the review actually, when we were just reviewing, we had a dog that we created with a .h, and still reviewing it, we had a .c++ file that we created that implemented some of the functionality. And then we kind of looked at the concept and we said, well, we got a sea dog, but now we have a poodle. Remember the evil poodle subclass that yipes and doesn't growl. The dog was growling, so we changed the behavior here, where we kind of said, here's a class, so we have the new class C poodle, public C dog, and this is, I think I got this far maybe, I said this is where the inheritance is coming into play. Without this, we're not doing any inheritance. When we start building classes from other classes, we have to specify, well, where did this class come from? So C poodle is our new class, and it's from C dog, and we're including the cdog.h file. We don't have to put the cdog.c++ file in here for reasons I just mentioned. So here we go, public, and we're going to create, this is the constructor that we're going to do for C poodle. So here's where we inherit from dog. We take the C poodle and we get in an X that comes in as a parameter. And so we're all going to create this from C dog. A poodle has been made instead of a C dog. So what we're doing here is essentially overwriting the default constructor of the base class with the implemented behavior that we're adding for the C poodle. So when we inherit, we get, and here's what's going on behind the scenes, what we get is the normal constructor activity that occurs in the base class. If we don't override it, all of the constructors will actually trigger for us. So when we create a new C poodle, we actually create a new C dog at the same time. So both constructors will trigger. Same actual behavior that happens in Java. So the trick around it is just to override the constructor. And when we override it, we implement some new behavior for it, so it doesn't execute. It doesn't say C dog, it says C poodle. So here's where the normal constructor stuff takes place. C poodle, integer x. The superclass's constructor here is mentioned after it with this colon, and this is the super constructor. And it's always called, in terms of this, by C dog in this particular case. So with the constructor in which takes an integer. So note, if you don't explicitly call these superconstructors, it looks for no argument constructor in the superclass, which we don't actually have. So that's why we specifically called it, because we don't have a default constructor. So we said, this constructor is going to override, it's going to call this one. And it's going to change the behavior, it's going to add, say a poodle was made instead of a dog. So we created a poodle that has the attributes and the methods of that of the C dog has. So there's a problem, and this is, I think where we may have stopped, I'm not sure, but created a pointer variable of my poodle is equal to new my poodle 3, and now the C dog, my poodle, and we're using this because we have pointers going on. Growl is going to print growl, but poodles yipe, they don't growl. So we override the methods so that we can change a poodle from growling to yiping. So when we override the method, we give the functionality to the class. In this case, we need to override the growl method, so we simply redefine the method. So here's a better poodle, and if there is such a thing. So, poodles and dogs. Is a poodle really a dog? It's like a cat. I don't know. Anyway, C poodle, public C dog is the same as before. Here's the default constructor. Here's void growl, another method that's going to be in here. And this is the poodle was made. And then here, this is the new part down here where we're going to override. Well, the way we override was just essentially create a new method body for it. And we say from C poodle, then growl. See, if C poodle declares its own method, it overrides C dog's method of the same name. So if we said growl P, we'd have two. We'd have growl and we'd have growl P. We add to the list of methods in the superclasses, subclasses. And here, if we say growl, we're overriding the method that already exists. So now when we tell the poodle to growl, it's going to yipe instead, because we have yipe being printed out instead of growling. So So we have the access words, very similar to Java actually, the public and the private. So we can restrict the access to the attributes. So normally we make all of the attributes private, and we make all of the member functions public, so we can manipulate and basically control who's changing those attributes. Public means everyone can see it. Private means only classes can see it. So here we have a bad design. Here's a bad example. It won't compile, actually. Class X, we have private myInteger, and it's trying to change myInteger here, which is not going to be. It's not going to be allowed because it's private, and we're using it as a public. We're trying to change the attribute out into the public, which is going to violate the rules. This one's working because we changed the keyword to public instead of private. So kind of demonstrating the point that if you make it private, you can't change the variables, can't access the variables, can't do anything with the data that is private out in the main program. Why private? It's used for security. Keeps other classes from changing attributes. Things like that. It's for design, forces the classes to use accessors and modifiers, as I maybe mentioned in the beginning of the class lecture. And it's used for encapsulation, so the class is complete to itself. And now all of the data is hidden inside of the class, so it actually supports information hiding as well, to a certain extent. So here's a memory trace, and this kind of goes along with our pointer stuff that we've been looking at so far. If we create two instances of dog, we have two pointers here, D1 and D2. D1 and D2 are going to be new dogs, so that should look familiar. We're allocating dynamically. And we're going to say D1 is equal to D2. So we have null being created when we created D1, D2. Now D1 and D2 are now equal. Remembering new opens up space and calls a class constructor. So we have D1, and then we have D2. So in terms of this memory space, it's not actually occupying the same memory space. What we've got now is a D1 that, to do a comparison between D1, does it equal D2? It's always going to come back with false. So basically what this is demonstrating is that you can't create two instances of the same object, assign the same values to each one of these. So if you notice, these are the D1 and D2 have the same values associated with them. They're never going to actually be equal because these are pointer addresses, and the D1 memory location is never going to be equal to the D2 memory location. So this always fails, actually, which is one of the interesting things, especially with pointer variables. You can't take any two pointer variables and have them equal. They're two different memory addresses. Every pointer variable gets its own unique memory address. So when are you ever going to have two of them to be equal? You're never going to have. If you followed the pointers and see if they were equal, then they could possibly be equal if they're both pointing to the same memory location, or both holding the same piece of information. So here, if we said D1 is equal to D2, we've taken D1, and now we have assigned D1 to point to the same memory as D2. Now we have two pointer variables all pointing to the same memory address. And now D1 and D2 are equal. And so when no one is pointing to this one over here, which means we've just created a piece of garbage. I think this is where I stopped, actually. I don't know, because this all sounds familiar to me already. No one is pointing to this one. We've created a memory leak, actually. This is called garbage, and it's referred to as a memory leak because now we can't use this piece of information. It already it's assigned, it's out there, it's a piece of garbage. The compiler might think, or the runtime environment might think we're occupying it, but nothing is pointing to it. So freeing up memory might be necessary to get rid of this unused memory, and it makes it available, brings it back into the free memory list. So the rule is never to set to null, so you want to use the delete operator. So when we use the delete operator, it deallocates. It does the opposite of new. So it takes to the pointer to an object. So from the usage from the previous example, we would delete D1, and it would go back and say, before we assigned it, we say delete D1, deletes the memory that D1 points to, and then we say, well, D1 is now equal to D2. And then we make it equal, and then all of a sudden we have two pointers pointing to the same memory address, and now this is gone. But if we change the pointer first, we can't delete it. It's inaccessible at one point because we've changed the pointer. So here's a summary of the inheritance concept. The benefits of inheritance: allows you to reuse the code, allows you to specialize classes, creates good design. Use the class name, colon, space, colon, and the class name to achieve this. This is how you're doing it. And you override methods in the in the subclass. And the comparison operator tests the same object in memory, does not check to see if it's the same instance. So object-oriented programming, in terms of putting the pieces together, this is trivial at this point, because the hard part was creating classes and inheriting from classes and stuff. And this is a very short section, so I'll end after this, which is about 10 or 15 minutes or so. So a programmer defines the attributes and the behaviors of the objects. Often the objects are modeled after real-world entities, we know that. And the approach is a function-based programming, very different than C++. So C and C++ are a lot different. And if you've ever taken another object-oriented programming class with me, you've seen this many, many times, the abstraction, inheritance, and that. Usually I switch it around and I call it a PI. So it's abstraction, polymorphism, inheritance, encapsulation, and PIE. Well, I got information hiding, I got an extra word in here. But essentially those are the main reasons for object orientation, supporting these characteristics. And actually, believe it or not, C++ supports it in a very similar way as Java. Java requires object orientation to be used. C++, you can do a functional-based programming along with C++. You can do C along with object orientation. And there's a lot of people that program in C++, they never create a class, then they've never done object-oriented programming. They've always been doing functional-based programming at that point. So the class is the object type, and it's of object type, and it's used the attributes and data members as we've seen so far. When creating an object, we define the class, and defining a class does not actually create the object, it just creates the implementation of it. When we create those objects, so those instances of those classes, we are actually doing what's called instantiation, which is why they call them instances. Instances of classes become objects. And this information hiding is basically the part of the public, the private, the protected. It lists the public data member functions. The interface to the class is its outer world or its main driver program. And that's where we keep things private that we want to be implemented inside of the class. The implementation of the class doesn't matter outside of the class, only the interface to the class matters. And we can have different implementations of the same specification, which is why we can have different .h files that correlate to different .c++ files, if you think about it. And use people classes without fear. You can use other people's classes as long as they have maintained the public interface correctly. War will end, poverty and illness will be vanished from Earth. Yes, and the world will go on and be a better place with information hiding. So, inheritance, as we've seen so far, it's possible to extend existing classes without seeing them. It's interesting because the Java language actually uses the extend word. So C++ is a little bit more complicated to look at. It's the same identical concepts. The only thing different is the colon in the name of the class instead of the word extend, which is interesting. Confuses people sometimes. You can add whatever behavior you want. When you override, you just redefine the method. If you redefine a method, you override the previous method. So if you have a class that represents a student, you can create new classes for good students, for bad students, for different types of specializations. And then we have the concept of polymorphism that's also supported. And this is kind of a side effect that is created. So the ability of different objects to respond to the same message in different ways. So in this here we can tell, and cout is actually polymorphic if you think about it. You can tell the cout function to print an integer, a double, to print out an object, print out anything you want. And that's really an example of how polymorphism is added into the language. And the public and the private, I just went over that a few minutes ago. It establishes our interface rules. So everything that's in a public interface is used out into the main driver program. It's public. And then we also have protected. So protected is visible with classes that are allowed to inherit from that class, but not outside of the class. So private is within the class, protected is within the class, but those classes that are inheriting from us can access our data, or our member function, so it's protected. We have a constructor, as we've seen so far. We also have what's called the deconstructor. So what ends up happening with a class, and we've seen with pointers today, we can allocate, allocate, allocate. If we don't deallocate, we say new, but we don't say delete, we leave memory out there that's inaccessible, that creates a memory leak, eats up all of our memory. The computer thinks we're using it, but we're really not, because we can't access it anymore. We just created it. So what ends up happening is when we start using pointers in classes, when the class goes away, we want the memory to go away too. So the purpose of the destructor is the exact opposite of the constructor. We don't have this in Java, because Java has built-in garbage collection. This is our garbage collector for C++. Instead, inside of the class, if we've allocated memory inside of the class, we're done using the class. Each one of those instances is going to allocate memory. And so the deconstructor is called when the object is eliminated. So only one has, there's only one of them, and it's the default, and it has no arguments. Because it's not something we call. We can't call the deconstructor. And how does it go? How does it get eliminated? Well, when the class goes out of scope, when the class gets removed, and this is the instance of the class, I should be saying, when the instance of the class is assigned to something else, well, we just create the default destructor, and we put all of our deletes in there. So delete this, delete this, delete this, and it cleans it up. It removes all of that memory for us, so it's no longer sitting out there. We have the accessing data members. This is kind of review at this point. We have the dot notation that we can get at for private data members and member functions and methods that we run. So accessing class methods, we use the dot notation for that as well, just like calling a function. And in this particular case, we have to think about scope. So we have class foo up here that has an integer I, and down here, in terms of integer sum, another function, we have another one that's using I, and we have two i's. So, which I is it? Well, in the case of this is basically talking about and showing you the concept of scope, and how scope is the local. So whatever I is associated with the inner function is going to be here, and whatever I is with the outer class is going to be out here. So this is where the scope resolution operator, or the class scope operator, comes in handy. So we can say the class name and the member function. And we use this when we start looking at, especially when we create a .h file and we start creating a .c++ file. We can have many different .h files that are being used. And we say, well, from this class, override this member function. From this class, override that member function. And then you're able to pick and choose which member function you're implementing or you're overriding in terms of your code. And here you can say, like as an example used without a method but used for as a variable, we can say foo scope resolution operator I, which is saying, this one here, out here we want this I. And we can use it in other instances, rarely used except for with classes, because when are you going to have a use for it? It's usually when you're working with classes. Method names for class, method names inside of classes. So you can actually put the prototype of the method function in a class definition, and then the actual definition of the method, the implementation is outside of the specification, because it's in the implementation class, and we're using the scope resolution operator to say what method we're overriding. So here's an example actually out here. You can say class foo, integer foo, colon sum. So inside of this, we have this integer sum, and we just said we have it as a prototype. And then out here, we're saying, in here, this sum, go ahead, give me the method body. Here's the method body to use for that. So, classes and files that we've seen so far, we separate them out. We have the definition. I call it the specification. Some people call it the definition that goes in the .h. And then we have the implementation that goes in the .c++ file, which is defined outside of the definition. Very conventional, no strict pattern. You don't have to do things this way, but this is how C++ does things. So it's not a bad idea to follow along with the best practice, I guess, of what the compiler is actually doing. Static methods. You know what? Someone remind me. I'm going to stop at this point because static and class methods deserve more time. And also, I want to talk about operator overloading next time. So I'm going to remember, actually. I'm going to remember that I stopped on slide number 83. I want to cover this because we're kind of running short on time for today because I only wanted to go for like an hour and a half. So next time, you can remind me. Slide 83. So slide 83 of lecture 3. We're going to talk about static and class variables along with overriding and overloading. So, because I wanted to take a few minutes to discuss the final exam schedule. So, those people who came in and left already, well, that's your problem. So, out on the website. So, if you watch it, if you're listening to this at home, shut the video off, you're done. So, for those of you who are taking the final exam, what we have going on here, we have our object-oriented programming class in C++ is going to be on 8/17. And it's from 9 o'clock in the morning till 5 o'clock at night. You don't have to show up for that entire time. I did have one student send me a message already. No. The exam will take about an hour and a half to 2 hours. You can take all day if you want. You don't have to take all day. All students, all times. Maybe I should have put here between 9 a.m. and 5 p.m. No groups, which means you're not going to order by your last name or anything like that. And you don't have to get approval to show up on different days. As an example, let's say you're in the HTML class and you're also taking the object-oriented programming class. You can show up on Monday 8/8 and take both exams together. Or you can show up, which is what everyone's going to do, show up on 8/17, the very last day, and take all of the exams together. Allot yourself about 2 hours per exam, though. They're all going to be multiple choice. It's closed book, closed note, closed neighbor, closed internet. One exam per student, per class. Yeah, I've seen it all. No pre-approval needed to swap the schedule around. Any questions? Nope. Did I go through it too fast? One more time? Well, the exam. This is out on the internet. This is out on bhacker.com. Should be. It should be out right in the front page. Actually, I put it right here. You don't have to look too far. And I say this is recommended. I'm going to expect students for this class to show up on 8/17. Students for software engineering 1 to show up on 8/10. And you don't have class on 8/10. I forgot to mention. If we're taking it, once 8/8 happens, we're in final exam week. So there's no class, there's no C++ class on 8/10. Believe it or not, it sounds stupid. It sounds like, why am I even saying it? I get people ask me questions. You'd be amazed. These are the questions they're asking. So, any other questions now that I totally discouraged you from asking questions? Yeah. Okay, we're done. See you next week. We have I forgot to say, next week we have a regular class. I'm going to finish up with static class methods, hit a bunch of miscellaneous topics, which we pretty much covered everything we needed to cover. The following week, 2 weeks from now, we have final exam review. So I'll have the exam with me, and I'll tell you what's on it. Well, tell you what to study for it. There will not be any programming on the exam, however, it's multiple choice. But I'll tell you what subjects to study. Study pointers, obviously, study classes, structures, stuff like that. But I'll have the exam with me. I can pinpoint certain things. We'll have our official review in 2 weeks from today. Okay, now I'm done. Go. I promise I'm not going to talk anymore. I'm done.